So at the end of the last video, we saw that if we put an electromagnet inside a magnetic field, we get something called the catapult effect. And we're going to draw on that. So we're going to first look at a rule we can use to predict which direction a conductor will experience a force if it's in a magnetic field and it has a current going through it. That's what Fleming's left-hand rule is for. So you have to remember to use your left hand, and you have to arrange your fingers and thumb like you can see on this diagram here. So you need to point your first finger in the direction of the field lines. And what we mean by that is essentially we need to point from north to south because that's the direction that field lines travel. So that's where we point our first finger. We put our middle finger in the direction of conventional current, or the direction that positive charges are going. And if you do both of those things, your thumb will tell you the direction that the object will, or the wire, or the current carrying wire in this case, will experience a force in. That's the direction you'll get a magnetic force acting on the conductor. Okay, so then if you go back and have a look at your notes and try this out. So you've put a current carrying conductor into your magnetic field, you'll see it does indeed give you the correct direction. But we're going to focus on how this applies to motors in this video, which is why it's entitled the motor effect. Okay, so first thing I want to look at more generally is the direction that a moving charge experiences a force from a magnetic field. Because remember, magnetic fields are created by moving charges, which means that if a moving charge enters a magnetic field, it's going to experience a force from that magnetic field. So there's a general rule we can look at for working out what direction it would experience a force in. So the magnetic force, sometimes called a Lorentz force, is always perpendicular to both the magnetic field lines and the particle's velocity. This is essentially what Fleming's left-hand rule is telling us, because our first finger is the direction of the field, our middle finger is the direction that charged particles are traveling, and the way we've set up our hand, those two things are perpendicular to each other, and the force, or our thumb, is perpendicular to both of those. So this is just an expression, essentially, of Fleming's left-hand rule. One key thing I would like to note at this point, though, is that if a charged particle is traveling parallel to the field, it will experience no force at all. So there's one scenario which you will have a charged particle in a magnetic field and it won't experience a force. It's if it's parallel to the field lines. Okay, so let's have a look at the direction that different types of charged particles will experience a force in a magnetic field. So here is a magnetic field. So these X's are showing field lines going into the page. So imagine like your face is like the North Pole, the page is like the South Pole, so the field lines are going down into the page. Let's put a positive charge moving up along the screen into that field. So what effect is it going to have? Well, this is where we're going to use Fleming's left-hand rule. So our first finger is going to point at the screen, and it's going to be at 90 degrees to your screen because the field is going into the screen. Your middle finger is going to point up the screen because that's the direction that a positively charged particle is going. So first finger is into the screen, middle finger is pointing out the screen. You'll see your thumb is pointing to the left of the screen. So that's the direction that the Lorentz force of the magnetic force is going to act. So you'll notice that that's perpendicular to the velocity. So the effect that's going to have is it's going to change the direction, but it's not going to change the speed of your charged particle. Okay, so that's our positively charged particle. What if we put a negatively charged particle into the field? Well, a negatively charged is going to do exactly the opposite of what a positive charge is going to do. So it's going to experience a force to the right and it's going to bend the other way. So that's the thing to bear in mind. So Fleming's left-hand rule tells you the direction a positive charge will experience a force. So if you have a negative charge, it's just going to do the opposite of that, like you can see here. Okay, so What if we zoom out a bit? So we've gone quite close in here, so let's zoom out and have a look at what this actually looks like. So if we're looking on a much larger scale, we would see the charged particle going in a circular path, because if the magnetic field and the velocity are perpendicular, the particle experiences a force at 90 degrees to its velocity. So it's going to go in a circular path because its speed isn't going to change. It's got a force that's perpendicular towards the center of the circle, and so it's going to go in a circular path. So this is what those two paths we drew earlier would look like if we followed them on a larger scale. We'd see them traveling in a circle like this. So now we can start putting those principles into a motor and having a look at how a motor works. So a motor is made up of a few key parts. It's got what we'd call a coil or a rotor. So this is a wire which will be carrying a current. And I've just labelled some parts so I can refer to them later on. It has an external magnetic field. So we're going to have north on one side, south on the other. And we'll have a connection to a power source. So this is where the current comes from. We've got a power source that's providing that current, and it's connected to the coil, so we get a current flowing. Okay, so these two green bits here are known as brushes. So there is not a fixed connection between the green and the black, but sometimes they are touching each other, and when they're touching, that allows a current to flow. Okay, so those are what we call brushes, and this part we call either a coil or a rotor in the middle, because this is the part that's actually going to rotate around. Okay, so given that this is the long side of the battery, conventional current is going to come out here, so I've marked that in purple, showing, so conventional current is going to go from A to B, and then from C to D, like you can see. Okay, so if we want to work out the force that's acting on different parts of the coil, we're going to use Fleming's left-hand rule, because we've got a current carrying conductor in a magnetic field. So if we apply it to side AB, so the field is going across from left to right, because it goes from north to south. Current is going from A to B, so my middle finger is pointing from A to B. This one's quite fiddly to rotate your hand around. So your middle finger is pointing from A to B, your first finger is pointing from north to south, so your thumb should be pointing downwards. So that's going to mean the side AB is going to experience a force downward there. Now side BC is not going to experience a force because the charged particles are travelling in the same direction as the field lines, same with AD. So the other side that's going to experience a force is CD. So our first finger is still pointing from left to right because it goes from north to south, but our middle finger should point from C to D, and your thumb should therefore be pointing upwards. So we can see the force on that side is going to be upwards. So we've got two forces that are acting to rotate the coil in the same direction, and that's what's producing the turning effect here. Okay, so a question we might ask is, why is it going to rotate rather than accelerate? And to look at this, we're going to look at a side-on view. Now I've changed the scenario, and I've got rid of the permanent magnets because they would just get in the way and overcomplicate the diagram. But they would still have to be there for this to work. So we saw that we have a force acting on each side of the coil, and the bit I didn't show on the diagram is that there is a pivot going through here. So there's essentially an axle that goes all the way through the motor, and that allows it to spin. So that forms our pivot. So in terms of why it doesn't accelerate, well, those two forces are equal and opposite. So the resultant force is 0, and therefore acceleration is 0. So it's not going to accelerate upwards or downwards or anything like that. However, the thing to notice is both forces in this case have a clockwise moment about the pivot, and that causes the coil to rotate. So that's why it rotates, because we've got a moment that's non-zero, but it doesn't accelerate because the resultant force is 0 here. Okay. So there's a final part that we haven't seen yet on a motor called a split ring commutator, and what we're going to do is we're going to explain what the purpose of the commutator does. But before I do that, I'm first going to show you what would happen if we didn't have one, so you can see what's going on. So the role of a commutator is to reverse the current in the coil every 180 degrees it rotates. Okay, and the reason we need to do that is we want to keep the coil rotating in the same direction. So if it's rotating clockwise, we want it to rotate clockwise all the time, or the other way around, if you like. So that's why the commutator is there. So let's see what would happen if we didn't have one. So I've cut out a lot of the unnecessary detail in here. So in the diagram, I'm saying we've got a field going from left to right. So north is over on the left, south is over on the right. And we've got a current going from A to B and from C to D because it's going around this loop here. And then there's a power source somewhere that I'm not showing. So we've got a complete circuit. So if we apply Fleming's left-hand rule, my first finger points from left to right. My middle finger points from A to B. So you can see AB is going to experience a force downwards. We apply the same thing to CD. The field is going left to right. Middle finger goes from C to D. So your thumb is pointing upwards. The force on there is up. So we've got an anti-clockwise moment here. So this is going to rotate anti-clockwise. All good so far. So let's do that. So it's going to rotate 100. Let's see what happens when it rotates 180 degrees in the anti-clockwise direction. Well, now our coil is going to look like this, because essentially B and C will have swapped places, but A and D will have swapped places. But we haven't changed the direction that current is flowing in our circuit. So it's still going from A to B and C to D. So let's apply the same logic again. So for CD, the field is going from left to right. The current is going from C to D. So it's clearly going to experience a force upwards. Apply the same logic to AB. It's going to experience a force downwards, which you'll notice is trying to rotate it back exactly where it came from. Because remember, it has just rotated around and now it's trying to rotate it back to its original position. So it's not continuing to rotate in the same direction, it's stopping and then rotating back the way it came, which isn't great if you've got a motor and you want to power a car or something. You don't really want your car going forwards, backwards, forwards, backwards, forward, backwards. That would be quite a pain. So let's have a look at a commutator and what it does. So a commutator looks something like this. The split ring commutator is this section at the top, and it's the part that connects to the coil, which we haven't shown on that diagram. So this part at the top is what's called the split ring commutator. So we can see that if we go onto our diagram, this one kind of is our positively charged side. This one is our negative charge side if we look at the connections to the battery terminals. So when the coil has rotated 180 degrees, you'll notice if I call this part A and I call this part over here B, A is now connected to the other side of the split ring. So once it's rotated 180 degrees, A is now connected to the other side, so this is going to mean that current is going to go the other way. So let's say to start with, current is going from B around to A, because it goes from positive to negative. Once it's rotated 180 degrees, A is now positive and B is now negative, so it's now going to go from A to B. So we've reversed the current, and the effect this will have is to keep the coil rotating in the same direction. Because if you reverse the current, you will reverse the direction of the force. So the forces will now keep it rotating in the same direction. So that's our split ring commutator, and that's how it keeps our motor rotating. Okay. So we've got a motor and we've now got a split ring commutator, so it's rotating in the same direction. What if we want our motor rotating faster? Or as another way of asking that is, what if we want to increase our turning effect? Well, we can do this by thinking about how can we increase the force on the coil, so the part that's rotating. Well, we could increase the strength of the external magnetic field. That would work. We could increase the current in the coil. That would also give us a bigger turning effect. And the final thing we could do is we could increase the number of turns or coils on the rotor. And actually, the turning effect, or the force, is directly proportional to each of these things. So doubling the field strength doubles the force. Doubling the current doubles the force. Doubling the turns doubles the force. And that's a useful rule to remember when you're applying things. But that's how we can make it a bigger turning effect, and therefore you end up with a faster rotation.